If you've ever seen that classic illustration of an apple falling on Isaac Newton's head and thought that was all you needed to know about gravity, I hate to break it to you. You're wrong. Gravity remains one of the most misunderstood areas in all of science. Sure, we can measure it, predict its effects, and even use it to send probes to other planets. But understanding what gravity truly is, at its deepest and most microscopic level, continues to be one of modern physics' greatest mysteries. And the deeper you dive into this subject, the stranger it becomes. Sometimes, it even feels almost magical. Gravity, for example, doesn't just keep you glued to the ground, it also influences how time itself passes for you. And that's only the tip of the iceberg. Studying gravity is like opening a box full of surprises that challenge our very sense of reality. It's no wonder that even after centuries since Newton and Einstein, the world's greatest minds still haven't completely deciphered this familiar yet deeply enigmatic force. It may sound strange, but despite being the force that governs the cosmos on the grandest scales, gravity is absurdly weak when compared to the other fundamental forces of nature. Take Earth, for example. Our planet has a mass of about 5.97 sextillion kilograms. That's a 5 followed by 24 zeros. And yet, the gravity it generates is so weak that you overcome it. Every time you lift a cup of coffee or stand up from a chair, think about that. You, an ordinary human being, can challenge the same force that keeps the moon in orbit. And speaking of the moon, even though it's much smaller than Earth, it has a massive influence on us, strong enough to move entire oceans and create tides. The rise and fall of a sea that we see at the beach is the result of a delicate dance between Earth's gravity and the moon's. But here's a fascinating paradox. How can gravity be weak enough for you to overcome it with a simple movement and at the same time strong enough to keep planets orbiting the sun and organize entire galaxies? That's just one of the many strange aspects of this mysterious force. To understand how peculiar gravity really is, we need to compare it with the other three fundamental forces of nature: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Technically, many physicists don't even like to call gravity a force in the same sense as the others. But we'll get to that controversy soon. Let's start with the absolute champion in strength: the strong nuclear force. It's responsible for keeping protons and neutrons tightly bound within the atomic nucleus. And that's incredible because protons naturally repel each other. They all carry positive charges, and like charges repel. Yet, the strong nuclear force is so powerful that it overcomes that electrical repulsion and holds everything together. In magnitude, the strong nuclear force is about 100 million trillion times stronger than gravity, virtually unimaginable. The only reason we don't feel its effects in our daily lives is because it acts only over extremely tiny distances, smaller than the nucleus of an atom. Next comes the weak nuclear force. Don't be fooled by the name. It's called weak, but compared to gravity, it's absurdly powerful. This is the force behind phenomena like radioactive decay, a process that's fundamental to nuclear physics and to the energy that powers the stars. Without the weak force, the sun wouldn't shine. It's responsible for enabling the reactions that turn hydrogen into helium in the sun's core, releasing light and heat. This force is mediated by particles known as W and Z bosons and acts at even shorter distances than the atomic nucleus, although it's about 1,000,000 times weaker than the strong nuclear force. The weak force is still 10 to the 25th power times stronger than gravity. Yes, a 1 followed by 25 zeros. Even at its microscopic scale, it plays a crucial role in the workings of the universe. Now we reach the force that governs our everyday life, electromagnetism. If we have electric light, motors, computers, and practically all modern technology today, it's because we learned to control this force. It's deeply connected to the properties of electrons and is mediated by particles called photons. Every time you flip a light switch or see a compass needle aligned with Earth's magnetic field, you're witnessing electromagnetism in action. Although it's weaker than the strong nuclear force, electromagnetism has something special. It acts over long distances, just like gravity. This property allows it to shape not only atoms and molecules, but also large-scale phenomena that we can directly perceive. In terms of strength, it's about 10 times stronger than gravity, another mind-blowing number. Want an example? Look at a simple compass. The fact that a tiny piece of metal can respond to the magnetic field of the entire planet shows how far-reaching and powerful electromagnetism really is. Now that we understand how weak gravity is compared to the other forces, it becomes even more fascinating to realize that it's the architect of the universe. Without gravity, there would be no galaxies, no stars, no planets, and certainly no life. The universe would be a chaotic void filled with scattered particles and no structure. The key to all of this lies in time. Gravity is like a patient, tireless force. It doesn't need to be intense. It just needs to act continuously for billions of years to turn chaos into order. Tiny particles began attracting each other, forming small clumps. Those clumps increased their mass, strengthening local gravity, which then attracted even more matter. This cycle, repeated over 13.8 billion years, gave rise to everything we see today. Planets, solar systems, and galaxies. And the process isn't over yet. The formation of the universe is still happening right now. As you watch this video, stars are being born, galaxies are colliding, and gravity continues to shape the cosmos with its almost infinite patience. Many people think of gravity only as that invisible force we feel on Earth, but its fingerprints are scattered across the universe. It's in stellar nurseries, where clouds of gas collapse to form new stars. It's in black holes, where its power is so extreme that not even light can escape. It defines the shapes of spiral galaxies and keeps planets locked in stable orbits. And here's another fascinating fact. Like electromagnetism, gravity has infinite range. No matter how far away you are, gravity is still there, acting even if almost imperceptible. Remember that famous line from Obi-Wan Kenobi, the Jedi Master from Star Wars? He described the Force as an energy field created by all living things. It surrounds us, it penetrates us, it binds the galaxy together. Well, if you replace living things with everything that has mass, you end up with a surprisingly accurate description of gravity. Like the Jedi Force, gravity is everywhere. It surrounds everything and connects the entire universe. The only difference is that, unlike Obi-Wan's mystical energy, we know gravity follows precise physical laws, even though deep mysteries about its true nature still remain. Now, talking about infinity might sound almost philosophical or even like science fiction. After all, very few things in nature seem truly limitless. But when it comes to gravity, its reach is theoretically infinite. That means any object with mass, from a grain of sand to an entire galaxy, exerts a gravitational influence on every other object in the universe. Of course, that doesn't mean you can feel the gravity of a star billions of light years away, because the force weakens as distance increases. Still, The idea that everything is gravitationally connected, even if but despite its limitless range, gravity isn't instantaneous. It can't travel faster than light. For example, both sunlight and the sun's gravitational influence take about 8 minutes to reach us here on Earth. That means if the sun were to suddenly vanish, which thankfully won't happen, we wouldn't notice its disappearance right away. We'd still see its light and feel its gravity for 8 full minutes before both were gone. Gravity also follows what's known as the inverse square law. This means that the force decreases proportionally to the square of the distance. In other words, if you move twice as far from a massive object, its gravitational pull becomes 4 times weaker. Move 3 times farther, and it drops 9 times, and so on. So while gravity never truly reaches zero, it becomes so weak at great distances that it's practically negligible. That's also why the largest masses in any region, like giant stars or black holes, dominate their surroundings, even if many smaller bodies are nearby. Now, you might be wondering, what about my gravity? Do I influence the people around me? Technically, yes. Everything with mass generates a gravitational field, including you. But in practice, the effect is so tiny, it's almost impossible to measure. Let's do a quick calculation. Imagine 2 people weighing 100 kilograms each, standing side by side. The gravitational force between them would be just 0.00041713 newtons, so small, it's completely irrelevant in daily life. And if you double the distance between them, that value drops to 1/4. In other words, the gravity your body exerts on another human is virtually zero compared to the forces that truly shape the universe. So far, we've seen that gravity is strange, but get ready. From this point on, it becomes downright bizarre. There's an effect that all objects with mass, including you, experience, even if you never notice it. We're talking about time dilation, a real phenomenon predicted by modern physics, but often misunderstood in practice. It means that time doesn't pass the same way for everyone. Depending on where you are and how fast you move, seconds can stretch or shrink. It's so counterintuitive that once you really understand what's happening, you realize that measuring time as something absolute and universal simply doesn't make sense. Einstein's general theory of relativity explains that time runs more slowly the closer you are to a massive object, like a planet or a star. That happens because gravity curves space-time and clocks, including the biological clock inside each of us, start ticking at different rates depending on where they are within that gravitational field. In practical terms, the closer you are to Earth's center, the slower time passes for you. The higher you are, say, on top of a mountain, the faster time flows. The difference is tiny, but it's real. For example, for every kilometer you climb in altitude, a clock ticks about 10 nanoseconds faster per day than one at sea level. It doesn't sound like much, but it's enough that scientists must correct for it. In high-precision systems like GPS, which only works properly because it accounts for these time variations. And here's another fascinating detail. Earth isn't perfectly uniform. The planet has different densities and irregularities, meaning gravity varies slightly depending on where you are. In theory, each of us experiences time just a little differently, but the story doesn't end there. Beyond gravity, speed also influences the passage of time. This is what Einstein called special relativity. A fascinating example comes from the International Space Station. At first glance, You might imagine that astronauts being about 400 kilometers above Earth, where gravity is slightly weaker, would experience time passing faster than we do here on the surface. But it's the opposite. The International Space Station travels at an incredible 7,700 meters per second, roughly 27,600 kilometers per hour relative to Earth. This speed produces a time dilation effect that outweighs the advantage of being farther from Earth's gravity. The result, time aboard the station passes just a little slower than it does for us on Earth. In practice, an astronaut who spends several months on the station returns, having lived about 0.007 seconds less than they would have on the planet below. It's a tiny effect, but completely real and measured with extraordinary precision. Up to this point, we've been talking about time variations so small they might seem negligible, but the point is, they exist. And when something exists, it can accumulate over billions of years. A striking example is the Earth's core. Being closer to the planet's center of mass, time there passes slightly slower than on the surface. The result, after 4.5 billion years, the Earth's core is about 2.5 years younger than the crust where we live. It doesn't affect our daily lives, but it reveals just how real and measurable gravitational time dilation is. Until now, we've treated gravity like it was a force similar to electromagnetism or the nuclear forces. But the truth is, it shouldn't even be on the same list. Gravity, as we understand it today, is actually the result of the curvature of spacetime. Imagine the universe as a vast elastic fabric. Place a massive object, like a planet or a star, and the fabric deforms. Other nearby objects fall into this deformation, not because something pulls them, but because the space itself where they move is curved. The famous analogy of a metal ball on a trampoline helps visualize this. The ball represents Earth, the trampoline represents space-time, but in reality, it's not just a simple depression on a flat surface. What occurs is a full three-dimensional distortion, almost as if space molds itself around the mass. This helps explain why gravity is so different from the other fundamental forces. One of the most fascinating aspects of this distortion is that it affects not just objects with mass, but even light, which has no mass at all. Normally, light travels in a straight line unless it encounters a medium like water or a lens, which causes refraction. But in the case of gravity, no medium exists. What changes is space-time itself. Light follows the straightest path possible within this curved space, which to us appears as a bend. This phenomenon is known as gravitational lensing and is one of the most striking confirmations of Einstein's theory. Thanks to it, astronomers can observe extremely distant galaxies, using clusters of galaxies as natural cosmic lenses. And when we realize that something capable of bending light isn't really a force in the traditional sense, but a feature of the universe's geometry itself, well, that's when the mind starts to reel. If you're imagining seeing light bend here on Earth, I'm afraid it won't be visible. Earth's gravitational effect on light is far too tiny to detect. But the good news is that the phenomena can be observed. We just need to look at far more massive objects and rely on powerful telescopes. When a huge concentration of mass, like a galaxy or a galaxy cluster, lies between a distant light source and us, its gravity warps the surrounding space. The result is that light from the distant source curves around this mass and reaches our eyes, seemingly coming from multiple directions, forming distorted images, or even a perfect luminous ring. It's as if the universe itself were using a giant lens to focus. Light. These effects aren't just beautiful, they're incredibly powerful tools for astronomers. Gravitational lensing allows us to study extremely distant galaxies, detect dark matter, which doesn't emit light but distorts space, and investigate how the universe expands. But as impressive as gravitational lensing is, it's still gentle compared to what happens near a black hole, where gravity reaches its most extreme point. You've probably heard that not even light can escape a black hole. Now, you understand why space-time curvature there is so profound that nothing, absolutely nothing, can escape beyond the event horizon. Not even photons traveling at light speed. What exactly happens to light and everything else that falls in is still one of physics' greatest debates. We know that space-time becomes so distorted that our equations no longer reliably describe it. Even the best theoretical models struggle to explain what occurs beyond this invisible boundary. And here we enter a realm where even the brightest minds get confused. The frontier between gravity and quantum physics. So far, we've been discussing gravity as Einstein described it, a smooth, elegant curvature of space-time that perfectly explains large-scale phenomena, planets,